Hello and thank you for joining us today. My name is Janet Richardson and I will be talking to you today about recent advances in sediment related to modelling, primarily focused on the use of increased resolution data in SciMap and Earth observation data. So as you could see from Dave's earlier talk, sediment within catchments can be a real problem. It can affect biodiversity by silting up spawning sites for salmon, for example. It can cause problems during flooding due to recreation areas being covered in silt, but it also contains a lot of other pollutants and can cause increased water treatment costs due to metaldehyde and microplastics. Erosion risk mapping is a way for us to model and map in our catchments where the sediment and soil is coming from so that we can focus our management efforts, for example, natural flood management techniques. A lot of people use SciMap for erosion risk mapping, and the risk of soil erosion is related to the availability of sediment, how erodible is the substrate. So in SciMap, this is related to your land use data, and then the connectivity to the system. Can the sediment actually reach the network? So if you have erosion in a distant part of your catchment and it will never reach the drainage network, this won't affect your WFD status. The connectivity to the system is calculated through the digital elevation model, the DEM, and rainfall. So as you can see from the previous slides, SciMap uses the digital elevation model, rainfall and land use as the data input, but there's a few limitations with this. So erodibility of the substrate is linked to the land use and not the underlying soil or geology. The static land use maps that people often use, those from CEH and Careen, do not actually show seasonal variation. So although they're based on satellite data, they show an average of the year and do not show up with bare land or when fields are left fallow. DEMs do not pick up artificial drainage, so those small drainage networks around fields that are often placed to help drainage. And rainfall is commonly the yearly average, which doesn't pick up peaks and troughs and extreme events throughout the year. As part of a fellowship with Yorkshire Water, we were looking at how we can increase the amount of data and resolution used in SciMap to see the differences in output and management decisions. So one of the ways that we can increase the resolution of the data for land use, for example, is by using Earth observation or satellite data. So the top image just shows the CEH land use map, which is a kilometre resolution, and the bottom image is satellite data of the Derwent catchment, which was our case study area, where the resolution is 10 metres. So using machine learning and Saga GIS and other open source platforms, we were able to create seasonal land use maps that would enable us to see when the land is bare. And this is really just based on the colour of the image. So a certain type of green is a forest, a certain type of brown is bare land, and blue, for example, for water. So you can train the GIS to pop this image out based on the underlying red, blue, green spectrum. So by using satellite-derived land use maps, we were able to create seasonal land use maps that can show the percentage change of bare land within the Derwent catchment. So we had maps for autumn, summer, spring, and winter. And you can see on these figures the output from SciMap. So where there's more red, there's more erosion risk. SciMap doesn't give you absolute values, it just gives you a relative risk within the catchment. So the main information here is in the red box where the difference between the CEH and satellite imagery is shown. And when there's reds and oranges, the CEH maps are relatively underestimating erosion risk during that time. So you can see that's quite apparent in the summer region for the whole catchment, and then in the autumn region for the upland areas. So by using this seasonal land use maps, we're able to use seasonal rainfall data, which enables us to see how rainfall tracks throughout the year, as well as how bare land tracks and how our management options may vary depending on the data that we use. We can also start to investigate climate change with this method. So if we can upload and input different climate change scenarios, so this is based on the UK CP09 projections, we can see that the erosion hotspots, those areas of red, don't really change throughout different climate change projections. So they're the same for the low emission scenario as they are for the high emission scenario. So the source areas through time are unlikely to change. However, it's likely the volumes of sediment will increase. As I stated before, SciMap doesn't give you absolute volumes. There's a lot of research that can be done in this area about average versus extreme events. So now that we have the new UK CP18 projections, for example, we may be able to see and model extreme rainfall events as compared to the average that people often model. We can also update our DEM by incorporating those artificial drainage networks that we discussed earlier. So the image here is just around Pickering, and the red lines are all the field drains around the farms and land uses, and then the blue lines are the main river networks. So to do this, you can artificially deepen your DEM in certain locations so that you can pick up these pathways that are often not incorporated into modelling. So a lot of erosion risk modelling is biased by the gradient, so you get more erosion in steeper areas. However, we've all seen sediment and movement of water and sediment on lowland areas. So by incorporating the artificial drainage network, this is one way to overcome the model. And this is the output of that. So just around in the Derwent again, you can see that there's slightly more erosion in the artificial network around these pathways. There's more areas of medium to high erosion. So by incorporating the artificial drainage network, that was not traditionally picked up on the DEM, and that's due to the drainage contributing area that you use. We can see a truer state of what's happening in our lowland areas, and this tries to overcome the bias in gradient that is within the models. So by updating our data that we use, by using higher resolution, Earth observation, and changing our DEM to represent what we truly see in the field, we can start to have better, more tailored management. So seasonal variation is not often picked up using traditional methods, as shown by the different DEMs that we showed earlier. The artificial drainage really needs to be incorporated to get a true representation. We often focus in the upland areas for sources of our erosion risk. However, lowland areas can be just as bad. Future work really needs to look at those smaller pathways, bank erosion and high intensity storm events, just to try and close the sediment budget within the catchment. So how much of it is from bank erosion or from gullies within forests, for example. One of the problems that we have with sediment is that we often don't know the baseline data within our catchments because there's not a historic data set, and a lot of our flow gauges don't have any sediment gauges. So one of the ways we can overcome this is in a model called SWAT, which stands for the Soil Water Assessment Tool. And again, the data input is very similar to that of SciMap, a DEM, land use. It also includes soil and daily flow, river and rainfall data. So from using this modelling, we can start to build up what we would expect for each parcel of land, how much erosion is expected due to the underlying physical properties. So we can simulate an annual sediment yield. And this is really important. So again, we can update our land use maps using satellite imagery. We can use higher resolution DEM data to make sure that we're incorporating our artificial networks. This will enable us to get baseline data. So when we're starting to move to the world of environmental land management and payment for outcomes, using different modelling techniques, we can increase the resolution of the data that we're using by using Earth observation. But we can also start to tease out the baseline data of how much is natural and what is actually expected from that land parcel. So recent advances in Earth observation have really allowed us to increase the resolution of the data that we're using to improve our modelling by looking at seasonal variation and increasing the different range of pathways that you can incorporate. So there's a range of possibilities. There's potential for remote monitoring, for example, so paying into our payment for outcomes approach. There's possibilities to help improve data resolution. So all the satellite imagery that we've processed so far is open access, using open access tools. So we can start to look at seasonal variation. So potentially this could work with farmers' businesses a bit better if they can put interventions in and then use that land for other means during the rest of the season when we know that there's a lower erosion risk. We can collect imagery after a flow event. So one of the big questions was, what does more of the work, the average events or the extreme events, and then how do those extreme events, how do the flow paths change? So by using drones, for example, we can go out and survey after a flow event to see if our pathways are different to what have been modelled. And by doing this, we can produce more detailed maps to help inform catchment management and to make sure that there's a longevity in what we do by incorporating the climate change projections.